Okay, so let's have a class, and we're going to directly jump into the lacto operon. Before that, we want to have some information will be introduced to you. So, this is we call post-transcription regulation. So this is what happened for the bacteria. Bacteria living in environments. Let's say they are coming with some of the amino acids. This is, we call it a stimulant. The stimulant which means it's going to track in the bacteria. So bacteria basically have a sensor in their cell wall system called a sensor. And then they will do is amplify. The amplifier will be response to what they sensory, and finally they will become transcription followed by translation. And this is needed the gene regulation. Okay, there is a gene regulation for that. This is what you talk about. There are so many called operon. That's what it is for. Okay, now, before we talk about the lacto operon, we want to give you an overall picture. What is talk about the post-transcription regulation? So this is we talk about structure gene. And we also call it a functional gene. So there is a standard model for structure gene. So let's do just like this. It's very simple. We have a couple boxes right here. There is a 3 box which is important. We call it A, P, and O. What is A position? Activator, binding position. What is P? Promoter. What is O? Operator. And you know that. What's a promoter for? The promoter, specifically in bacteria, have a very special conservative sequence, which is PA, GA, CA, and PA, TA, AT. So this is called minus 35, this is called minus 10. And this is a special conservative sequence will be recognized by a sigma factor. We talk about sigma 70 of RNA polymerase will be combined, and it started to do the transcription. Okay, that's what happened. So let's say this is RNA polymerase. Now, this comes out with a regulation. We have 2 sides. The right side go this way, we call it downstream. And the left side is go this way, we call it upstream. Anything happened on the right side, this is called negative control. And anything happened on the left side is called positive control. Now, they also have 2 different types of the negative control and the positive control, which is encoding, we so-called inducible and repressible. And the same thing, the positive control will be encoding inducible and repressible. So what happened is we give this, we could talk about it again. So negative control. So we could draw here, which is APO. Originally, there is an inhibitor attached to the O position. It is an inhibitor. And right now, I have something, another chemical, could attach here. And they will change the morphology of the inhibitor to let it not attach to the O. And the RNA polymerase will be attached to the promoter. Therefore, the transcription starts. This is called inducible negative control. And this chemical is called inducer. Now there is another situation will happen is still this three position. Originally, I don't have anything attached to the O position. So RNA polymerase will be attached to the promoter. So the reaction will happen, which is the transcription will happen. However, I have some chemical combined with the inhibitor, then we attach to here. And this attachments will not happen and the transcription will be stopped. This is called repressible. And this chemical, we call it co-repressor. Please do not talk there. Oh, okay, because other students will be, need to listen. Okay, I know these things you learn in your genetic classes or other classes. So we just want to talk about here. Okay, so these called negative control. Now, what are the two examples here? This first one is lacto-operon. We will talk about it real quick. The second one is tryptophan operon. And this is the one we will not talk, but you learn in your other classes. Okay, so this is negative control. Now, positive control. We will do the same thing, which means APO, and this is also the APO. So, originally, we have something attached to the A. Okay, then RNA polymerase will be attached to that, transcription will happen. And now, right now, I have an inducible. They will be there to in the opposite direction. Originally, there is an activator right here. Okay, they need some inducible gene to attach to it, and then this whole thing can go attached to the A position, and the transcription will happen because RNA polymerase is attached to the B. This is called positive inducible regulation, and this is the example is maltose operon. And in other words, there is something else with originally there is a repressor goes there, and the reaction will be happens. But right now what happens is a co-repressor goes here, let these things not attach to it, and the transcription will not happen. This is arabinose operon. So here you can see it is very interesting, is inducible. Basically is talk about is catabolism, which means you are using the energy, and the repressible we are talking about is anabolism, which means you're going to biosynthesize some of the chemicals. This is some overall picture when we talk about the post-transcription regulation. We only going to talk about the lactose. These three things we're not going to talk. You learned in genetic classes already. We don't pay much attention to that because this regulation we could talk about the whole, almost whole semester, and for the genetics class, like a month at least. Okay, so we're going to only talk about is lacto-operon. So lacto-operon. Well, what I draw on the picture here is actually the slides 1 and the slides 2, 1 and 2. Okay, this is lacto-operon. So we want to talk about the lacto-operon, what it is. First of all, lacto-operon is created by Jacob and Manon in 1930s. It is originally started from E. coli. So it is a well-known operon related to lactose, whether we're going to use it or not. Okay, so before we go this way, we need to talk about the lactose and the structure. All these things, and you can understand. So what is lactose, first of all? Okay, I have a glucose. OH. I have a glucose. H, OH, OH, H, OH. Right here is important. H, CH2, OH. This is the glucose. Glucose combined with another chemical very similar to glucose. You can understand it is an isomer. Everything, the chemical looks exactly the same. The only difference is at carbon number 4, this hydroxy is go down. And this is go up, and this is go down. The only difference is right here. And here. Okay? This is H, CH2, OH. Now what they do, they can connect it with each other. Once they connected with each other, I'll just draw a brief one, okay? I'll just draw a brief one. So this here, I'm not going to do a whole thing. So you have CH2, OH, right here CH2, OH. So this is glucose. What is this one? Galactose. And when they combine, becomes the lactose. And here it's called 1,4-glycosidic bonds. That's what's the structure of lactose. Lactose is important. You know that. Some of you cannot drinking or eat lactose because it will cause lactose intolerance. We'll have a diarrhea after that. That's a lactose. Now, we have glucose, we have lactose. They also could be reacted, have another direction. Instead of they have 1,4-glycosidic bonds, they could react it with here. So we'll create a chemical. Here's another very interesting one. So let's draw this here. Okay, so CH2, OH. They will connect it right here. This is called a 1,6-glycosidic bonds. And we'll generate a chemical called allolactose. This is a side reaction. So this is some basic knowledge you need to know. And this happens in a bacterial cell. This is the basic knowledge you need to know. Okay, now we're going to talk about the lacto-operon. Let's talk about this guy first. So this is lacto-operon, what it looks like. We can draw a couple of location. And this is P is promoter, O is operator, C is cap. This is called cap, catabolite, activator, protein. And downstream, you will have 3 functional genes, lag Z, lag Y, and lag A. Okay, what is lag Z? Beta glycosidase. If you see very clearly, we have here. Oh, sorry, lactose permease. Yes, glycosidase. Glycosidase. What is lag Y? Is lactose permease. What is lag A? This is transacetylase. Okay, what's the function of lag Z? This is beta glycosidase. They need to create 1,4-glycosidic bonds. They already said it is glycosidase. Obviously, they're going to have the reaction, which is glucose and the lactose. They will become a lactose. Glucose and the galactose will become a lactose, or go the other way. Okay? Now, what means the permease the second way? Lactose permease. You think about this is a bacteria cell wall, and the lactose has to come in. They need permease. This is like a permit, or to let you come in. Transacetylase, the function is unknown. We don't know about that. Okay? So that is a very basic structure, what it looks like. So this is happened. A very simple way to explain the lacto-operon. So what happened is, originally, there is something attached to the O position, the operator position. This is an inhibitor. They attach to it. What the inhibitor looks like? The inhibitor is a tetramer. It looks like this. It also could look like that. It's a tetramer, and then they attach to it. So the O has 3 positions. It could be attached to O1 and O3. It also could be attached to O1 and O2. So it will be looks like this. And if we talk about the secondary structure of the tetramer, it is helice turn and helice structure. So there's originally an inhibitor attached to it. This will happen if no lactose present. And if the no lactose present, the tetramer will attach to the O position, so the RNA polymerase cannot attach to the promoter, and the translation will not happen. And this is easy to understand if there's no lactose. But how about if we have a lactose? If we have a lactose, this inhibitor here, they will be attached by allolactose. So allolactose here is an inducer. They will attach to it and then change the morphology. Once it's changed the morphology, this inhibitor will be gone. So let's just say like this. This inhibitor there. Okay, I have allolactose. is coming, they change the morphology, and this is gone. This is no longer attached to it. Then what happened? The RNA polymerase will be attached to the O position, and the lag Z, lag Y, lag A will be translated because transcription will happen. Then they started to create glucose and galactose, because lactose can be used. This phenomenon, we already talked about that. In the enzyme function, this is called allosteric effect, which means there is some chemical on the side of the enzyme, and then they inhibit and they change the morphology to let them not attach to the O. So the remaining question will be, where are the first lactose comes? This is a question when I asked my professor when I first heard about this. And he told me he doesn't know, but there is something similar. It's the same question asked, the chicken and the egg, or birds and the egg, which comes first. So the reasonable answer is, in the bacterial cell, they more or less have some allolactose, which means the inducer is already there. So the inducer can be connected with the repressor. The inducer is already there. They can connect it with the inhibitor, change the morphology, let them not attach to the O, so the reaction will happen. Because RNA polymerase will go to attach to the promoter. But if there is no lactose, this guy will be in a very minimal level. Okay, so that's a very simple way we explain the lacto-operon. So this is what the picture talks about here. You can see no lactose. The inhibitor will attach to the operator, so the transcription will not happen because RNA polymerase is not attached to the promoter. Once there is a lactose